Hi all, let's take a look at section 10.4, which primarily deals with alternating series. Anytime you have an alternating series, you're going to have that -1 to the n power. That's going to cause terms of your series to alternate in sign from negative to positive to negative to positive. Now, the first concept that we're going to be talking about in this section is the concept of absolute convergence. And all that is saying is that your series would converge even if it didn't alternate in sign. So sometimes the series will converge simply because it's alternating in sign from negative to positive to negative to positive, and those terms end up canceling each other out. But the concept of absolute convergence is it's saying that a series is going to be absolutely convergent if the absolute value of that series converges. Now, the absolute value, that would just get rid of any alternating sign. So you don't care if you have a -1 to the n or -1 to the n plus 1. If you have an absolute value around it, every term is going to be positive anyway. So it's saying that the series would absolutely converge if clearly the absolute value of the series general term converges. Now, conditional convergence is going to say that a series a sub n converges, but the series of the absolute value of a sub n diverges. So the only reason it's converging is because the term is alternating in sign. So now I can say, well, all right, in this case, a sub n would be conditionally convergent if the series converges, but the absolute value of the series diverges. Now, in all of our alternating series tests, we'll either use what's called the alternating series test or the Leibniz test. Different books call it different things, but either way, it's a very simple test. It's just saying that the alternating series, if you have -1 to the n power times a sub n, that series is going to converge if the limit as n approaches infinity of the general term, and notice that general term is not including the -1 to the n, so if the limit as n approaches infinity of that general term is 0, then you can say, well, then the whole series will converge. Now, when we look at determining convergence of an alternating series such as my first problem here, I have -1 to the n minus 1 power, as n goes from 1 to infinity, of 1 over n to the 2/3 power. Now, since it's an alternating series, that's my very first thing here is I notice the -1 to the n minus 1 power, so I can go in and say, well, okay, then the alternating series test tells me I can take the limit as n approaches infinity of the non-alternating part, so I'm taking the limit as n approaches infinity of 1 over n to the 2/3 power. And I can see as n goes to infinity, 1 over infinity to the 2/3 power is going to be 1 over infinity, which has a limiting value of 0. So therefore I can say this series, -1 to the n minus 1 over, times 1 over n to the 2/3 power, it's a convergent series. That series converges. Now you'll see I put however. So just because the series converges doesn't mean you can't think about more with these alternating series. I was thinking hypothetically, what if that series didn't alternate in sign? So if I think about the absolute value of that series, which I talk about up here, well, the absolute value of that series would do away with that -1 to the n minus 1 power. And so I would say without that, it's just the series 1 over n to the 2/3. And instantly you know, hey, that's a divergent p-series because the denominator is not getting large enough fast enough for this function to converge to any value. So you can say, well, that's a p-series with p equals 2/3. And remember, the decision for convergence in the p-series, anytime p is a number less than or equal to 1, it diverges. If p would have been greater than 1, it would converge. So this is a divergent p-series with p equals 2/3. Now, what does all this mean? Well, I showed in the first step that the series converges due to the alternating series test. However, if you're looking at the absolute value of the series, it's a divergent p-series. Well, this is the whole concept of what I talked about up here about a series being conditionally convergent. We say for this number 1 Therefore, this series, negative 1 to the n minus 1 times 1 over n to the 2/3, converges conditionally. The words converges conditionally, all that means is, yes, your alternating series does converge. But the only reason it converges is because of the alternating sign. If that alternating sign was not there, it would be a divergent series. So you say, well, okay, it's not a divergent series though, because the alternating sign is there. Therefore, we say this series conditionally converges or converges conditionally. Now, a second problem I want to look at with you. What if I ask you to determine the convergence of, again, it's an alternating series, from n equals 1 to infinity, negative 1 to the n times n to the 4th over n cubed plus 1. Well, again, alternating series, so I'll use that alternating series test where I say, okay, it will converge if the limit as n approaches infinity of a sub n is equal to 0. But notice, in this problem, even if you ignore the alternating part, you still have n to the 4th over n cubed plus 1. You know as n goes to infinity, this fraction is going to go to infinity because you have a larger power of n in the numerator. It's going to be infinity over 1. It's going to go to infinity. So any limiting value that's not 0 is going to show that this alternating series diverges. So in order to be convergent, that limit would have to be 0. Well, clearly infinity is certainly not 0. So we can say, since the limit as n approaches infinity of the general term of our series is not 0, that is conclusive evidence to show that our series diverges. And you could either say this is by the alternating series test, or like I have in red here, you could also just say, well, this diverges due to the test for divergence, or the divergence test. The divergence test, if you remember, all it says is if you try to plug in the limit as n approaches infinity of a sub n, if it's not equal to 0, then the series diverges. Now, if it is equal to 0, it doesn't say it converges. The alternating series test would tell you it does converge if the limit as n approaches infinity of a sub n would equal 0. But either by the alternating series test or the divergence test, clearly I can say it's not 0, therefore this diverges. Now, one other problem in this section, and you'll notice this section is short. There's only 8 problems in the homework assignment for this section. My next one I want to look at here, it's technically not an alternating series, but it kind of behaves like an alternating series. If I ask you to determine the convergence of the series from 1 to infinity of the sine of pi n over 4 divided by n squared. So think about this with me. In this numerator, if n is 1, you'd have the sine of pi over 4, which is square root of 2 over 2. If n is 2, it'd be the pi over 2, it'd be 1. So this function is going to go from a numerator of square root of 2 over 2 to 1, back to the square root of 2 over 2, then it would go down to 0, then you go to the negative square root of 2 over 2 when n is 5. At n equals 6, this would go straight down to negative 1. So all you're doing is you're going around your unit circle in increments of pi over 4 and telling me what the sign is. So the numerator, it could be 0, square root of 2 over 2, 1, back down to 0, back down to the negative square root of 2 over 2. The lowest it could ever be is negative 1. Now, that lowest it could ever be is negative 1. The highest it could ever be is 1. But it could be certainly a bunch of other numbers other than that as well. 0 and square root of 2 over 2 and negative square root of 2 over 2. So that kind of leads it to a problematic point. It's not quite an alternating series, but it's similar to one. So here's what I'm going to do. I'm going to consider the absolute value of the general term of this series. So let's consider that. Well, the general term would be the absolute value of this sine of pi n over 4 divided by n squared. Now what I know is that the maximum value the sine could ever take on is a maximum of 1. Sometimes it's going to be the square root of 2 over 2, sometimes it's going to be 0. But the maximum it could ever be is 1. So I know even the absolute value of this general term, it is strictly, and I say strictly, but here I have less than or equal to 1 over n squared. This is a true statement. It would also be true to say it's strictly less than 1 over n squared. Either way is fine. Here I have less than or equal to 1 over n squared. Now, what do you already know about 1 over n squared? Well, we know that the series 1 over n squared is a convergent p-series. Remember, anytime you have n to the denominator raised to a power, it is a p-series, and the test for convergence there is anytime p is a number greater than 1, then that denominator is large enough to make that fraction small so that whenever you're trying to sum up from 1 to infinity, you're going to get a convergent finite answer. In this case, we say this is a convergent p-series because p is equal to 2, which is greater than 1. Now, since that series converges, and I've already shown that the absolute value of the general term of the series I'm interested in has to be less than that. So I can say, since the absolute value of the sine of pi over 4 over n squared is less than or equal to 1 over n squared, that's evidence that the series, the absolute value of the sine of pi over 4 over n squared, converges by the comparison test. Remember the comparison test, if you're less than the general term of a series that converges, then that's evidence that that series also converges by the comparison test. Now, back to the original series, if the absolute value of that series converges, that is clear evidence that the original series converges. And we would say that this shows that the series of sine of pi over 4 over n squared from n equals 1 to infinity converges absolutely. So you don't even need to show this individual function. If you can show the absolute value converges, you've already showed that this converges, and we say it converges absolutely because even if the signs didn't alternate, it still converges. So when the signs alternate, it definitely converges, or we just say converges absolutely. Pretty cool problem. Let me know if you have any questions with any of the homework assignments in this section. They're pretty straightforward once you get used to it, but it does take some getting accustomed to. I'll be glad to help you out with that.